Hi everybody, welcome back to the channel. In this video we're going to take a look at parametric equations, and specifically we're going to look at some examples about how to be able to eliminate a parameter and some common mistakes that I see. So first of all, when we talk about parametric equations, you should have already seen something about this. This should not be an introduction video for you. But the idea of parametric equations say that x is some function in terms of t, has a t in it somewhere, and y is some function that has a t in it somehow. And we're using t because we're thinking about time. So we can take a graph and think about a function that you already know about that has an x and a y in the equation. And the idea here is not just what does the curve look like involving x and y, but really the idea is where are you on the curve at a specific time t. So what I would recommend is when you plug in, like let's say for example that x is maybe 2t plus 1 and y is t cubed plus 5. I don't necessarily know that these equations match up with this graph. I don't think so. But the idea being, can you create I guess maybe poorly named in this case, we usually call them a t-table, but that's usually only when there's two columns. Now if there's three columns you can kind of relabel, where you have a t, an x, and a y. By the way, the t in the t-table has nothing to do with the variable t, it just, the table looks like a big T. So you can plug in plug in values of t, like 0, 1, 2, and figure out what do you get for x, what do you get for y when you plug in a value of t, and you get specific x, y pairs, and those are still the coordinate pairs that represent the points on your graph. But now what I would encourage you to think about is wherever you are as an xy point, you're at a specific time. And so what I like to do is put a little person on my graph and think about kind of what time is it that they're standing right there, and then as time goes along, where are you on your graph? And maybe as time goes along, you get this point and this point when you plug in t equals 1 and t equals 2 and t equals 3. And so as t gets bigger and bigger and bigger, the question is which direction are you going? So sometimes a graph will have little direction arrows on here, and I like to think about this person kind of walking along the curve in a specific direction, and that's the idea of parametric equations. Again, shouldn't really be something new for you, but in this video I want to focus on how do you take a set of parametric equations and get rid of t so that you can write the equation in terms of just an x and a y. Because if we can do that, we can graph this in our calculator a lot more easily, and we understand a lot about how this graph looks. So take a look at this example. I've given you an example of a set of parametric equations here. Let's keep in mind I'm talking about t greater than or equal to 0. I think for this example we could also talk about negative values of t. I don't see any domain issues over here where you're not allowed to plug in negative values of t, but that's okay. We'll use t as greater than or equal to 0, and that means we might only have a part of what the whole curve looks like, but that's okay. We're talking about specific times, only positive time values. Okay, so let's go ahead and you could make yourself a little t-table like we did earlier. You could say, you know, plug in a value of t and figure out what do you get for x and what do you get for y, and plot some points on there, and that's perfectly fine. But I think another thing you could do is you could think about, how do I get rid of t and only have an equation that involves x and y? And so sometimes books might use a phrase like eliminate the parameter to be able to describe this situation. And there's one way that is probably should be maybe a go-to method, almost one of the first methods you think about. It's not the only method we're going to use. We're going to look at 3 different examples in here that all kind of use a little bit of a different method. But what you should be thinking about in here is using something that you've used in your past to solve a system of equations, which is substitution. Okay, so let's use substitution in this example, and it's actually not the only method we could even use for this example. If you remember back when we talked about a system of equations, you could use substitution. You could actually use elimination. Okay, just a little glimpse into what that would look like in this problem, if you took the bottom equation and multiplied everything by 2, or maybe a negative 2, now you'd have a 6t and a negative 6t, and you could add the two equations together. The t's would go away, and you just have an equation that only involves an x and a y. That's another strategy as well. You could also use substitution in here, and here's what that would look like. Take one of your equations, I don't really care which one, and solve for t. I'm going to do that in the y equation. So we have x equals 6t minus 4. Go ahead and take the second equation and solve for t. Get t by itself. Okay, so let me go ahead and remove my t table over here that we didn't use to clear some space. Go ahead and take your second equation, y equals 3t, and solve for t. So divide both sides by 3, so you get y over 3 equals t. And now substituting says where you see a t, go ahead and replace a t with a y over 3. So the top equation becomes x equals 6 times y over 3 minus 4. There's actually an equation that doesn't involve a t anymore. Technically, we did follow the directions. Technically, we do have an equation right now that only has an x and a y in it. We did eliminate that parameter of a t, but really we should probably simplify this as well, right? This is x equals, let's see, 6 and the 3 can cancel. You're left with a 2y minus 4. And really, in an equation like this, because we like to graph this in our calculator, it probably would make a lot of sense for us to try to get y by itself even in this problem. You don't have to. Technically, this is a perfectly fine example of a linear equation, but since we typically get y by itself, let's go ahead and do that. So x plus 4 equals 2y, and then go ahead and divide both sides by 2, and you get something that looks like your nice slope-intercept form here. Y equals 1/2 x, or you could say x over 2, plus 2. And so there's your line that you should have graphed, or you would have been able to graph if you had given yourself a little t-table in there and plot some values of t. But not only do you get this line, but now based on t, you can say which direction you should be going along that line as t gets larger and larger. Okay. Now, substitution and elimination are both good strategies. Those are both good approaches, but they're not the only approaches we could consider. Okay, we have also seen a lot of trig now, and really in your past when you looked at systems of equations, you probably hadn't seen a lot of trig at that point, because usually you talk about systems of equations in kind of an algebra class before you even see a lot of trig show up. So once you have trig, you could say, how do I solve something like that here? Can I do the same thing? Can I take one of my variables or one of my equations and solve for t? I'd get something like y over 3 equals the sine of t. Hey, can't I just take the inverse sine and get t all by itself? Well, yeah, sort of. You got to be a little careful with that, though. Remember our discussion about how when you have an inverse trig function, you got to be careful about which quadrant you're in. And now that if you do it this way, which we're going to see in a second, there's a better way. But if you do it this way and you get t by itself, now you're thinking about taking that top equation and substituting in for t where you have what t is equal to. And so this is the cosine of the inverse sine of y over 3. That gets a little weird. Okay, that's pretty messy. You'd have to do something like this where I don't know, you could try this. You could do something like this is alpha and create a triangle and talk about the sides in the triangle, and that gets a little bit messy. I think there's a better approach. Okay, I think there's a better approach. Let me go ahead and erase a lot of this here and kind of give ourselves a better way. Okay, the better way that we're going to have is from trig, and it's something you better have remembered from trig. So let me bring up something from trig that you definitely should have in your back pocket, or probably more like front pocket, because it's so useful. Something like the cosine squared of, I'm not even going to call it x this time, how about the cosine squared of t plus the sine squared of t? You should remember this one off the top of your head. That's equal to 1, right? Okay, so let's tell you what, let's take the two equations that we have, and instead of just manipulating one of them, let's manipulate them both. Go ahead and get the cosine of t by itself and the sine of t by itself, and then what we're going to end up doing is using this Pythagorean identity. So if you do that, here's what that should look like. You should get something like x over 2 equals the cosine of t, and y over 3 equals the sine of t. Now, go ahead and take those two equations right there and square both sides of both equations. So you get x over 2 squared equals cosine squared of t, and you get something like y over 3 squared equals the sine squared of t. Okay, now we said earlier that substitution and elimination are good strategies. Go ahead and use kind of like the idea of elimination here. Go ahead and add both these two equations together. Look at what you get on the right side. Now that we've squared both, we had isolated the trig, we isolated cosine and sine, and now that we squared both sides, now we have a cosine squared and a sine squared. When you add those together, on the right side you should just get 1. And then on the left side you get something like x over 2 squared, but you can actually write that as x squared over 4. And then you can't really combine that with the y squareds. The best you can do is kind of leave it like this, y squared over 9 equals 1. But again, what we've done is we just eliminated the parameter, we got rid of the t. Now we have an equation that only has x's and y's in it. In fact, this one should look pretty familiar. Think back to your conic days. This should look something like an ellipse, and you should be able to tell me a lot of information about the ellipse. You should be able to graph this and come up with a lot of the features. Okay, so just a strategy. I'm not saying this is going to work every time, but it's just something really good to look out for. If you have a problem that has cosines and sines in it, a cosine of t and a sine of t, it might be a good thought for you to think about getting cosine of t and sine of t by itself, squaring both sides, and then getting and then adding together so that you have a cosine squared of t plus a sine squared of t, and you can use the fact that that's equal to 1 on the other side. Okay, so again, I'm not saying this is going to work for every approach. I'm just trying to put tools in your toolbox to say the goal is to get rid of t. How can I do that? There's multiple strategies. These are just a few of them. One last example here. You have something like this. Okay, and so if we have something like x equals e to the negative t and y equals e to the t, you might say something like, well, what could I do with these? And so one way you can think about this is you could actually change the way the top one is written. You could change it as x equals, since it's a negative exponent, e to the negative t, you could actually write that as 1 over e to the t, and then y equals e to the t as well. This is, again, still like elimination, but I'm worried that when I say elimination, some of you just think adding two equations together or subtracting two equations. Depending on the type of function, we got to get a little bit more creative. That's why in the last problem we had to square both sides after we got cosine and sine by itself, and then in this one we're going to get a little more creative as well. Can you think about a way to combine a 1 over e to the t and an e to the t so that the t's kind of cancel out or go away? Don't add these two equations together or subtract these two equations. What if you multiply these two equations together? Okay, if you multiply the two equations together, you get 1 over e to the t times e to the t on the right side, and there you go, you get just 1 on the right side. And then if you multiply on the left side, you get x times y, and that's a little bit weird. We've seen examples like this. This is a conic that is kind of rotated somehow, but again, remember the goal of these problems, though, was to get rid of t and to get an equation that only has an x or a y all by itself. Okay, now again, you could go ahead and you could actually go ahead and move the x over to the other side. You get something like y equals 1 over x. So we know a lot about what that looks like. That is a rational function, and which for us is an example of a rotated hyperbola, essentially. So just again, another strategy for you to look out for. Now, I want to just talk for really briefly about how to be able to graph these. Okay, so I'm not going to make a whole video about how to graph parametric equations on your calculator. There are tons of good videos about how to graph parametric equations on your calculator on YouTube here. Go ahead and check those out. I'm not going to go make a separate one just for this. But graph parametric equations, I'll give you just kind of a quick scoop, is if you go to your mode button, I think your fourth option down should say something like function, and then I think it says PAR, and then POL, and SEQ. And we are almost always, so far, been in this mode, function mode. But polar mode, back in Chapter 8 for us, you could use this polar mode for the problems in Chapter 8.1, 8.2. If you want to graph a parametric equation now, go ahead and put it in this PAR mode. And then when you go to your y equals, it's not going to say y equals anymore. Now it's going to say x equals something and y equals something. And you might say, well, how do I type a t in? If you look at the X button on your calculator, the X button actually says X, let's see, it's X, T, theta, and N. And so that X button actually uses all four of those letters depending on what mode you're in up here, because T deals with parametric mode, theta deals with polar mode, and N deals with sequence mode. So you can graph parametric equations on your calculator. Okay, hope you've enjoyed.